Good morning, everybody. Happy Tuesday. I'm going to give people just a minute to join before I start. While we are waiting for everybody to join, let me do a quick little screen share of a couple things. So just real quick, your schedule for the week, fairly light. Wednesday, Wednesday lab 9 is due. That's the lab that you did last week. Hopefully many of you uploaded it already, but just Wednesday uploaded by midnight. And then Friday, PLC number 12 is due, must be completed. You just need to upload it. So basically I had sent out an email. It's unclear whether or not the state is going to require us to turn in those TBA forms. It's still sort of up in the air, but just in case, your PLC this week is just filling it out. If you can, print it out, fill it out, take a picture, sign it, take a picture, upload it. If you don't have a printer, you can just enter it right into the Word document. Okay, and just real quick, sorry about canceling Zoom lecture yesterday. I did upload another lecture. I'm not feeling super well, so I might just keep this a little bit shorter than usual. All right, let me do a little recap of just what I've covered so far in chapter 12. I've done basically 2 lectures on it. So first, started talking about the cross product or vector product. Remember, dot product, the end result was a scalar, but cross product, the end result is a vector. And the way we define the magnitude of the cross product between 2 vectors is the magnitude of the first vector times the magnitude of the second vector times not the cosine, but the sine of the angle between the 2 vectors. That gives the magnitude, and the direction is given by the right-hand rule. And that's basically with the fingers of your right hand, you curl the first vector A into the second vector B. Your thumb is going to point in the direction of the cross product. So that's how you would do it if you were just given sort of 2 vectors where you were given the magnitude and the direction of each vector. But if you were given the vectors in IJK notation, then I went through this little shortcut for figuring out the cross product. And you're basically forming a 3x3 matrix where across the top you got IJK, and then the X, Y, and Z components of the first vector, and then the X, Y, and Z components of the second vectors. And in essence, what you're doing is just creating a 3x3 matrix, figuring out the determinant of that matrix. And I kind of went through in the first lecture how to do that. It's just a simple procedure to follow. Then I started talking about the different angular quantities. So we really have 3. So instead of our position in meters, when we're talking about angular quantities, position, we're basically using theta, and it's measured in radians. Instead of our linear velocity in meters per second, now we're looking at our angular velocity, and that's in radians per second. And instead of linear acceleration, we're talking about an angular acceleration in radians per second squared. Let me stop this just for 1 second and mute everybody for a second. Mute all. Allow them. All right, let's share the screen again. So this is a really cool little animation, and it's just showing that as these things are rotating, a couple things I want to point out. We're dealing with a rigid body, which means all parts are sort of fixed. I don't have different things moving at different angular speeds. Something like the sun would not be considered a rigid body because different parts of the sun can actually rotate at different rates. But as this is rotating, a couple things. One, let me let this thing rotate. Angular velocity, for this one, is just showing it in degrees per second. We measure it in radians per second, but that's just how quickly something is rotating. So a bigger angular velocity just means it's rotating faster. Smaller angular velocity just means it's rotating slower. And in general, things that are rotating counterclockwise, we consider that to be positive. And angular velocity, which is negative, would be something which is rotating clockwise. And a couple things to see about this. One, what we're going to see is as this rotates, all parts of it are rotating at the exact same angular speed. Let's make this slower. But what you'll see here is V is representing the linear speed. Even though these are rotating at the exact same angular speed in radians per second, they're not moving at the same linear speed. And I kind of went through relating linear and angular quantities. I'll review that again. Let me just look at this other rotation one. So this is kind of cool. So here you've got ladybugs, and let me just hit go. So right now, they're not moving. If I give it an angular velocity, now you can see they are both rotating. And actually, let me just clear this for a second. Let's start this with an angular velocity, and let's give it a negative angular acceleration. So one, just in terms of signs of the velocity and acceleration. Just like before with linear quantities, if something is speeding up, then velocity and acceleration point in the same direction, they have the same sign. If something is slowing down, then velocity and acceleration point in opposite directions, they have opposite signs. So here, if I have something with a positive angular velocity, but a negative angular acceleration, what that means is it's starting out rotating in the positive direction, which is counterclockwise, but the rate at which it's rotating is slowing down. So let's play this, go. So you can see it's rotating counterclockwise, but because it's accelerating in the opposite direction, it's slowing down. Eventually it's going to stop. And if the acceleration remains constant, it's going to then reverse directions and then start speeding up in the opposite direction. And just like with linear quantities, if I were to take the slope of the position, the angular position versus time, that would give me the angular velocity. And if I were to take the slope of the angular velocity versus time, that would give me the angular acceleration. Okay, let's go back to these notes again. And I'll talk just about relating linear and angular quantities. So as these ladybugs are moving, so let's say they rotate from here to here, they are both going to move through the exact same angle. So, but if I look, this ladybug, as it rotates through that angle, is going to cover much less distance than this one. So even though they're rotating at the same speed in terms of radians per second, they're not traveling at the same linear speed. So in terms of relating the angular quantities, the three things that are going to be important is my tangential speed is given by r times omega. R is how far away from the axis of rotation you are, and omega is just the angular speed in radians per second. My my tangential acceleration, and remember this is acceleration because of a change in speed. This is given by r times the angular acceleration. And my radial acceleration, which if you remember is given by a change in direction, not a change in speed. Remember, it was equal to v squared over r, but you can also show that that equals to r omega squared. So this is how you would relate linear quantities to angular quantities. If I'm told how quickly something is rotating in radians per second, and I know how far it is from the axis of rotation in meters, then I can tell you how fast that object is moving in meters per second. And that's kind of what I've covered so far. So let me just stop this for a second. I want to just open it up quickly to any questions on things that I have covered so far in chapter 12. Oh, going once. Going twice. Removing the recap. Putting on the, I don't know, what do you want to call it, cap. Okay, let's do a screen share again. So what I want to talk about today, a few things. First one is the center of mass. If you remember, pretty much up until today, we have been treating everything as particles. Now, if I consider a real object, and let's just say I were to throw an object through the air, what you would see is the motion is somewhat complicated. But I can simplify it greatly if I look at what's called the center of mass. And the center of mass is just the average position of all the mass of the object. So let's just say I shot an object up at a certain angle, and we were to analyze it using projectile motion. Well, if we're just talking about a particle, we've done that before. Well, what happens if instead of a particle, let's say I were to throw a pen or to throw a baton? What I would see is the center of mass of the object follows the exact path as if I just threw a ball or something like that. But in addition to the center of mass just traveling like we would if I threw a ball, it's also going to be rotating about the center of mass at the exact same time. So the center of mass basically behaves like a particle whose mass is equal to the entire mass of the object. So this is a little hard to see, but this is a baton which was thrown in the air. And this red dot, or this red line, shows you the position of the center of mass of the baton. So this position would be exactly the same as if I threw a ball that had the exact mass of this baton. But in addition to the center of mass moving, it's also going to be rotating at the same time. Another kind of cool thing is, let's say I had a bullet or a bomb or something like that that I shot up in the air and it exploded, and there was no air resistance or friction. If I were to look at all these pieces and look at the center of mass of those pieces as they're falling, even though these pieces may be broken up into lots of little ones, if I figured out the average position of these pieces as they're moving, the center of mass would move just like a particle going through space. Okay, so this video is not really showing, but this was a video of tossing a hammer. And right here, little dot was the center of mass of the hanger, or the hammer. And what you would see is as this hammer was moving, it was basically moving, and the dot was moving in a nice parabolic path, but the hammer is rotating about the dot as it moves. Okay, one thing I want to point out about these lecture notes that I posted is I realized that these lecture notes went from April 18th, 2019 to April 25th. So somehow the lecture notes that I got from this person, I'm missing a few days. So what I did is I posted up here more lecture notes. These are basically my own lecture notes that I was using to lecture on. And so they're sort of in addition to the other lecture notes. So let's talk about center of mass. So like I said before, the center of mass is just the average position of the mass of an object. So if I were to look at how the mass is distributed, center of mass is just the average position of the mass. And for an unconstrained object, meaning an object that's not made to rotate on an axis or pivot, if there's no external forces on it, no net force that's, well, what's going to end up happening is an object which is not constrained to move on an axis, if I were to just throw it in the air, it will naturally rotate about its center of mass. That's just how it works. So I throw a pen in the air, that pen is going to naturally rotate about its center of mass. And the position of the center of mass is just given by this equation, where you're looking, it's really a weighted average by mass. What it is I take big M is the total mass of the object. And what I'm doing is, so this would be for a collection of particles. So, you know, let's say I had 5 particles here. Let's just make it a bunch of particles. Each one of these particles has a different mass and a different position. Center mass. Hold on 1 second. They're doing yard work outside. I'm sorry if that's loud. So really, you're just doing a weighted average. So what you're doing is, if I had a collection of particles and I wanted to figure out what is the center of mass from an object, what I would do is I would just take the mass of each object times how far it is from some origin, and then I'm dividing by the sum of the masses. Same thing for y. So what I get is the position of the center of mass is m1 x1 plus m2 x2 plus dot 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 divided by the sum of the masses, and my position of my center of mass in the y direction would be m1 y1 plus m2 y2 plus dot 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 divided by m1 plus m2 plus dot dot dot. Now the question is, what is x1, what is x2, and so on? Well, I can define my origin anywhere. And x1, x2, x3, that's how far that particular particle is from the origin. Now, it doesn't matter where I define the origin. When I go and I calculate the center of mass, it'll always be in the exact same position relative to the object. So let me just do a simple example, and maybe that'll help clarify. What do I want to do? Example problems.
Back to that slide. Can we go back to that slide real quick?
That slide, what was I looking at? I'm totally...
Sorry.
Yes.
Yeah, that's the side bracket with the, oh man, the center of mass equations.
Yes.
Set of, I can't read that word.
Set of... this is for, sorry, this is for a set of particles.
Particles. Okay.
So one, let me just throw this out in advance. For a solid object, which you end up having to do is you end up having to do an integral. And it's kind of weird because your book goes through this, but you never ever actually calculate any integrals. We're only really calculating the center of mass for a collection of particles. And I don't know if you've done this in your math class yet, but let me just throw one thing out here because it's kind of cool. For a solid object, if you notice, this integral is an integral with respect to mass. How the hell do you integrate with respect to mass? And the answer is, you probably know from previous classes that the density of an object is equal to the mass divided by the volume, which means the mass of an object is equal to the density times the volume. And what ends up happening is I can turn my integral with respect to mass into an integral with respect to volume. And this would be true if the density of the object is constant. So what you end up doing is you end up doing a volume integral. If we're talking about a spherical object, it'd be r squared sine theta dr d theta d phi and so on. But we're only using this equation to calculate the center of mass of a collection of particles. So going to this example problem. Problem 12.6. It says 3 masses shown in the figure are connected by massless, rigid rods. What are the coordinates of the center of mass? So what you're going to do here is really define where you want the origin to be. So I'm going to define my origin. Let me make this a little smaller. As right here where mass A is. And so the position of my center of mass, I've only got 3 objects. So it's going to be, let's just use A, B, and C. MA, XA, plus MB, XB, plus MC, XC, divided by MA, plus MB, plus MC. So in this particular case, And here we can just stick with grams because I have grams on the numerator, grams on the denominator. So I have mass A is 300 grams. The position of A, since my origin is here, is just going to be 0, plus the mass of B, which is 200 grams. The X position of B is 0 also, plus the mass of C. Make this a tiny bit smaller. Plus the mass of C, which is 100 grams, times X position, which is 10 centimeters. And then I'm dividing by the sum of the masses. So I'm dividing by 300 grams plus 200 grams plus 100 grams. And if you calculate this, what you're going to find is that the X position of the center of mass is 1.7 centimeters from where I've defined my origin, which means the position of my center of mass, is going to be somewhere over here. Now, let me just throw this out here. If instead I chose my origin to be right here, I would still get the position of the center of mass to be in the exact same location. It's going to have different X and Y coordinates, but for a collection of objects, the center of mass is going to be at a certain position in space. If I define my origin to be slightly different, the X and Y positions will have different values, but the center of mass is always going to be right here for the X. Now let's do the same thing for Y. It's going to be MA times YA plus MB times YB plus MC times YC over MA plus MB plus MC. So in this case, mass of A is still 300 grams. What is its Y position? Well, again, I've defined my origin to be where mass A is. So the Y value is 0, plus mass B, which is 200 grams. Its position is 10 centimeters in the Y direction, so 10 centimeters. And then plus C, which is 100 grams, and its Y value is 0. And then I'm dividing by the total mass, so 300 grams plus 200 grams plus 100 grams. And what you'll find if you do this calculation is 3.3 centimeters. So my center of mass of this collection of objects is 1.7 centimeters to the right of the origin, 3.3 centimeters above it. So it's about right there. And it doesn't matter where I define my origin. I defined it as here. So my X and Y positions are given relative to that. But if instead I define my origin to be here, this would still be the location of my center of mass. It would just have different X and Y coordinates. Okay, so I want to give you a chance to just try that with a relatively simple one. Let's take a look at, actually I want to say one thing real quick because this can sometimes be a little confusing. It looks like since mass A has a position of 0, mass B has a position of 0 in the X direction, that they are not affecting the position of the center of mass. But the truth is, because I'm dividing by the sum of all the masses, even if something is at a position of 0 relative to the origin, it's still going to affect the center of mass of the collection of objects because ultimately I'm dividing by the sum of all the masses. Okay, so going back, click your question. So the X and Y coordinates of the center of mass of this 3-particle system shown below are, so here they're giving us the origin. We're defining our origin right here. So actually, I want to just give you a minute or two. I'm going to work on it right now, solving it, but try and do that with me as I'm going through it. So we want to know what are the X and Y coordinates of the center of mass of this 3-particle system. So X, and I'm not going to talk as I'm doing this just to give you a chance to work on it on your own. Oh, what's going on here? X center of mass. So this is going to be, and let me just, I'm going to label these 1, 2, 3. So we have M1, X1 plus X2 plus M3, X3 all over M1 plus M2 plus M3. So I've got 4 kilograms times 0 plus 5 kilograms times 3 meters plus 6 kilograms times 1 meter all over 4 kilograms plus 5 kilograms plus 6 kilograms. So what do we got? 0 plus 15 plus 6. So we got 21 divided by 15. X position is 1.4. So we only have 2 possibilities. Now what we need to do is just calculate what is the Y position of the center of mass. And let me do that up here. And let me just skip writing out the equation. So it's going to be, whoops, M1 times Y1. So 4 kilograms times 0 plus M2 times Y2. Y2 is 2 meters plus 6 kilograms times Y1, which is 3 meters, divided by my total mass, which is 15 kilograms again. What I'm going to get is what? 0 plus 10 plus 18. So 28 divided by 15, 1.9. So the correct answer is 1.4 meters, in the X direction 1.9. So my center of mass is somewhere around here. Now the center of mass, no matter where I define the origin, would always be in that position. All right, let me stop this. I see a bunch of comments. Confuse me. Is it? Oh, so CM is center of mass or COM. Confuse me for a second. 1, 2 positive is mentioned twice. 1.4 also wrong reasoning. Okay, so let me just pause for a second. What questions can I answer about center of mass? We good? All right, go back to screen share. So one other thing I want to just say about this center of mass is, if I have a solid object and there is some axis of symmetry, the center of mass of a solid object will always sort of be along the axis of symmetry, which if you haven't had so far in math, don't worry about. But what that means really is, let's say I had a solid object, stick or something, or why can't I think? Whatever that is. If you've had math, axis of symmetry is basically, if you look, it looks exactly the same on one side of the axis as the other. So like for a solid object here, I would have an axis of symmetry right through the center, another axis of symmetry through the center here. So if this had a uniform density, meaning one part wasn't any more dense than the other, then the axis, this would be the center of mass. And just because of the reality of how we're doing this online course, we're not going to have super complicated problems. But when I'm dealing with an object like this, and let's say I were to use conservation of energy, and I had an object which started in some elevated position and then it fell. And I wanted to know, let's say I wanted to use conservation of energy or something to figure out how fast it's going. When I'm looking at the change in gravitational potential energy of a solid object, the one point I look at is how does the center of mass of the object change? So like if we were doing some sort of conservation of energy problem, I would define my initial position to be the position of the center of mass. And then as this object rotates, the center of mass is falling a specific distance. That's how much the gravitational potential energy of the entire object would change. Okay. I think what do we got? 15 minutes. I think the only thing else I want to cover today is rotational energy. And let me just go real quick to this. Oops, stop share screen. I want to go back to this ladybug thing for a second. So as this thing is rotating, one, not including these little ladybugs, the center of mass would probably be, whoa, well, that's cool. I don't know what I just did. As this is rotating, even though the center of mass of this is not moving through space, it has what's called rotational kinetic energy. So as an example, all the pulley problems we've been doing, we've been considering the pulleys to be massless. One of the things about that then is it doesn't have any rotational kinetic energy. But a real pulley, which is rotating, has a form of energy called rotational kinetic energy because all parts of it are moving. And what we do to figure it out is, what I would do is break this rotating object up into thousands of little particles and look at the kinetic energy of all of those particles combined. So going back to new share. So what I have drawn here is, let's just say I've got this weirdly shaped object. And it's rotating about some axis, and it's rotating counterclockwise. Well, let's just look at, let's say, 3 or 4 particles on this object. So let me do a different color. Whoops. Well, you know what? I have this thing right here. Why don't I just do it here? So this is where the object is rotating about. And this is just 3 of the many particles that make up the object. Right? This is kind of what you do in a lot of physics and math. If I want to look at a solid object, I treat it like a bunch of little particles and I add up all the particles together. Well, these particles are these particles are all moving through space. So as this thing is rotating, you know, this particle is rotating, this particle is rotating, this particle is rotating. But rather than think of it as rotating, it is moving with some linear speed. And remember, the way we relate my tangential speed to my angular speed is r omega. So here, then, the kinetic energy of this object, and I'm calling it the rotational kinetic energy, it's the sum of the kinetic energies of all the little particles that make up the object. So let's just write 3 of them, plus 1/2 m3 v3 squared. And in reality, this would almost be like an infinite sum, which we would actually end up integrating. But right now, we're looking at it as a collection of a bunch of particles that as this thing rotates, they're all moving. Well, I can relate the linear speed. Oh, that looks ugly. What is that? The linear speed to the angular speed. Let me just correct that for 1 second. And one of the key things about a rotating object, if it's a rigid body, all parts of the object are rotating at the exact same angular speed in radians per second. So I'm going to write this as, for each one, I'm going to write V1 as R1 times omega, V2 as R2 times omega, V3 as R3 times omega. Now I'm not writing omega 1, omega 2, omega 3 because they all have the exact same angular speed. So then instead of V1, I've got R1 omega. Instead of V2, I've got R2 omega and so on. Well, since omega is the same for everything, I can factor it out. And so instead of 1/2 m1 r1 omega squared plus 1/2 m2 r2 omega squared, I'm factoring out all of the m's and r's. Omega is the same for each. The 1/2 is obviously the same for each. And what I end up with is my kinetic energy of rotation is equal to 1/2 times this sum over all the object, or over all the particles of m sub I r sub I squared times omega squared. So r sub I is the distance of that particle from the axis of rotation. So if this is my first particle, r1 would be this distance here. If this is my second particle, r2 would be this distance. If this is my third particle, r3 would be this distance. Well, this almost looks like my kinetic energy term of 1/2 mv squared. And keep in mind, for every linear equation, we have a corresponding angular equation. Well, instead of linear speed, I have angular speed. This sum of mr squared must be like some rotational equivalent of mass. And it is, and it's what we call the moment of inertia. So we give it the symbol I. It's called the moment of inertia. And it is the rotational analog of mass. Rotational analog of mass. What it really depends upon is not just the mass, but how the mass is distributed. So the more mass I have farther from the axis of rotation, the harder it is to rotate that object. So the equation for the moment of inertia is given by the sum of mr squared. So if I had a collection of particles, I would sum up the mass times the radius squared of all the particles in the object, and that would be the moment of inertia. The units of I are kilograms meters squared. There is no special name for it. And one important thing about the moment of inertia is it's always given relative to an axis. So for example, if I had a rod, I could rotate the rod about an axis passing through one end, or I could rotate the rod about an axis passing through the center. They will not be the same in terms of how hard they are to rotate. The more mass you have farther from the axis of rotation, the harder it's going to be to rotate. So here, if I have an axis through A, or if I have an axis through B, you can see through A, I have more mass farther away from A than I do relative to B, which means my moment of inertia about an axis passing through A is going to be greater than my moment of inertia about an axis passing through B. That's if I have a collection of objects. Now, in reality, kind of like before, if I had a solid object, you would never in your right mind do a sum over billions and billions of particles that make up an object. What I do is this sum of mr squared becomes an integral, and it becomes the integral of r squared dm. And again, the way you would do this mathematically is this would be an integral of r squared times rho dv. And then how you would do dv is dependent upon whether you're doing cylindrical coordinates, rectangular coordinates, or spherical coordinates. If there were more time, I'd do a couple of these moments of inertia that I'm going to show you because the math is pretty cool. But these integrals that you get by integrating it, for specific kinds of objects, you just have sort of the results of the integral. So let me just tell you the ones that are going to be important. So for a thin rod about the center, the moment of inertia is given by 1/12 ml squared, where m is the mass of the rod, L is the length. If I have a thin rod about one end, it's 1/3 ml squared. You will use those fairly often, but the ones that come up all the time are these two. For a cylinder or disk with an axis through the center, the moment of inertia is 1/2 mr squared. you are going to use that for pulleys. We're pretty much going to model any pulley like a disc, and the center of, or the axis is always going to be through the center of the pulley. So the moment of inertia is 1/2 mr squared. And then the other one is a solid ball. For a solid sphere, so we're going to look at on Thursday objects rolling. A rolling object has kinetic energy, and the rotational part of it, the rotational kinetic energy, depends upon the moment of inertia. And for a sphere, it's 2/5 mr squared. So summarizing all of this, I don't know if I'm going to do a parallel axis theorem. So we had kinetic energy of 1/2 mv squared. I'm not sure if I said this at the time, but we consider this translational kinetic energy. So this is really the center of mass moving through space. So anytime I have a solid object which is moving through space, it has this rotational kinetic or translational kinetic energy. I also have a rotational kinetic energy, which is 1/2 I omega squared. This is just pure rotation. Meaning, if we are looking at this ladybug, as these ladybugs are moving, the center of mass of the entire system is not moving, but it's rotating. This rotating object has kinetic energy called rotational kinetic energy, and it equals 1/2 times the moment of inertia of the object times the angular speed squared. And just as a little preview, what we're going to look at on Thursday is a rolling object has two forms of kinetic energy associated with it. The center of mass of the object is moving through space. Well, let me look at the clicker questions real quick. Not clicker, PowerPoint. A rolling object can be considered a combination of two different forms of motion. One, pure translational motion of the center of mass. So this is a ball which is rolling, and there was a light attached to the top of the ball and a light in the middle. And what you're seeing is as this ball is rolling, the center of mass is moving through space. And because of that motion, there's a 1/2 mv squared term for the kinetic energy. But at the same time, the ball is spinning. That spinning ball has rotational kinetic energy. So there is a difference. If I had, let's say, a ball which was just sliding without rolling, it would have a kinetic energy just 1/2 mv squared. If I had an object which was just rotating but not moving, it would have a rotational kinetic energy of 1/2 I omega squared. This is translational. But if, I don't know how to draw something that just, well, it's tough to say, but a rolling object is a combination of, this is hard to see, oops, translational kinetic energy 1/2 mv squared. So I can consider a rolling object to really be a combination of the object just moving through space without rotating, the object just rotating, and I put those together, and that's really what a rolling object is. And that's what I'm going to cover mostly on Thursday, is looking at, let's say, where are we? If I had, and we're going to basically do conservation of energy. If I had a box sliding down an inclined plane, I'm going to get a different result as if I had a ball which is rolling down an inclined plane. A sliding box only has translational kinetic energy 1/2 mv squared. But a rolling ball has translational kinetic energy 1/2 mv squared, but it also has rotational kinetic energy 1/2 I omega squared. Booyah. Okay. Before I officially sort of stop lecture and open it up for office hours, The integral is for solids, yes. And let me just, again, we are not going to be doing any integrals in this class. Even if I was teaching this live, I might do an integral just because the math is really interesting, but that's not a major focus. Can you go over what is due this week? Hey, that's just what I was going to do. So let's share the screen and online resources. Okay, couple things. Only 2 things due this week. Wednesday, lab number 9 is due. That's the lab that you did last week. Just upload it to physics or mastering physics by midnight. And then Friday, PLC number 12 is due. And it's not a real PLC in a sense. It's just you filling out the TBA forms and then uploading it to mastering physics. Keep in mind that your TBA hours cannot be during lecture and they cannot be during lab. So just try and be mindful of that. I'm not 100% clear whether or not they're going to require us to send this to the state because everything's topsy-turvy, but I want to be prepared just in case. Let me grab this chat. Can you go over what is due? The TBA hours are lab hours, or so the TBA hours are the PLC hours. If you remember, every week you're required to put in 50 minutes in the PLC, and then I didn't really care if it was exactly 50 minutes. What I cared about was just getting the PLCs checked off. The state is requiring us to basically show that everyone is doing the TBA hours. So this is just something that I'm going to send to the state if they want it. Last thing I want to talk about, Wednesday, tomorrow. So we've got, what, 3 Wednesdays left. I am not doing any more labs where I'm filming the lab and then you're doing it. I'll talk about this tomorrow when I just preview it. You will have 2 weeks to basically create your own do-it-yourself lab from home using equipment that you have at home to create some kind of cool experiment looking at something that we've covered in Physics 4A. John and I have created 7 or 8 different possible labs that you could do, but you can come up with your own. And it's going to be kind of interesting because you don't have force sensors. Many of you don't have scales that you can measure things in mass, kilograms and things like that. But you can create your own homemade units. For example, most people have rubber bands. One of the experiments we have that you could do is, does a rubber band obey Hooke's law? Well, you know, for a rubber band, well, for a spring, the force exerted by the spring is equal to negative kx. So the bigger the force, the more the spring should stretch. So one idea would be, let's say you had a rubber band at home. You could test to see whether or not a rubber band obeys Hooke's law. How would you do that? Well, you'd have to have a bunch of objects that all have the same mass. So maybe a pennies. And I could just hang, let's say, a penny from a rubber band, see how far it stretches, and then hang 4 pennies from a rubber band, see how far it stretches. It's going to be something where you're going to have to be a bit creative. John and I are still working out all of the details. I'll let you know tomorrow. But on tomorrow, I will upload a short video sort of talking about what you're going to be doing. But you'll, in essence, have 2 weeks to do some sort of at-home experiment. And we're going to give you the option of either writing a formal report on it, doing a 5 to 10 minute video where you just send me the video, or the best, what I hope a lot of people would do, is the very last Wednesday of classes, which is going to be 2 weeks from tomorrow. My God, is you doing a Zoom presentation of your work. So this will be a formal report kind of grading. It'll be worth 20 points. You have 2 weeks to work on it, and it's just an at-home experiment that you're designing yourself to investigate something that we've covered in Physics 4A. All right, let me stop this. The lecture portion of today is done. Bring in office hours. Thank you, everybody who joined me live. I'm going to hang out for 25 minutes. If people have any questions, please let me know. Thank you, everybody. Questions I can answer.
Hey, Joe, this is Peter.
Hey, Peter.
I just had a question about, can we get our lab, I think it was lab 3, the last formal report, can we get that emailed to us as a PDF so we can see what we may need to do differently for the personal lab?
The answer is unfortunately no, because I had somebody helping me grade those labs and I can't go and pick them up from them.
Got it. Okay.
So, but one other thing also, some people wanted to know about their grades on, oh, that's tomorrow. So I have calculated where everybody stands right now. And just so you know, the class average for the current grade is an 85.1. So people are doing very well. A ton of A's, a ton of B's, a ton of C's, only a couple people are not passing. So I will let everybody know where they stand tomorrow. But let me just say I'm behind on the labs. So
Okay.
the grades that I give you tomorrow will be class participation, PLCs up until yesterday, only the first few labs, but your quizzes, your celebrations and everything, it should give people a good idea of where they stand.
Got it. Thanks a lot.
You're welcome.
Hey Joe,
Yes.
can you do an example of the cross product? Is it the cross product?
Yes.
Yes. I wasn't able to see that lesson, and I saw you just uploaded it yesterday, I believe, right?
No, that one was a couple days ago. But yeah, I can do an example. Was there an example? Online. You know what? I'm just going to make one up. And in fact, let me do that under cross product again. So I'm going to share screen, cross product 3. So if you haven't, if you didn't see any of the cross products, one, I would kind of go through it a bit, but what I gave you is just sort of a memory device for how to calculate the cross product if you're given X, Y, and Z coordinates of 2 vectors. And what you're doing, have you had matrices at all?
No, not yet.
Okay, so well, without going into a matrix, I gave you a little just memory device, and that's, where is it? So a 2x2 matrix. So if I just had, and don't even worry about what matrices are, but it's almost like a little memory device. If I had this 2x2 matrix of A, B, C, D, the determinant of a matrix, which is in a sense kind of like the absolute value, what I'm doing is taking whatever's in the upper left-hand corner and multiplying it by whatever's in the lower right-hand corner. So it's AD, and then minus whatever's in the upper right, minus whatever's in the lower left. So minus BC. This is just how you would define the determinant of a 2x2 matrix. And again, this is linear algebra. If you haven't had it, don't worry about it. But as an example, if I just had this 2x2 matrix with 3, 4, 1, 5, the determinant of it would be 3 times 5 minus 4 times 1, which would end up just being a number 11. Well, if you're doing a 3x3 matrix, what you do is, in essence, you turn that into 3 2x2 matrices. So what you do is you start with the very top right, and you get rid of the row in the column that A is in. And what you're left with is this 2x2 EFHI. And then B is next. You get rid of the row in the column that B is in, and you're left with DFGI. But one thing, and this just comes from linear algebra, there's a minus sign there. And that's just something you just need to memorize. Or I mean, you can put it on your cheat sheet. And then you go to C, you get rid of the row in the column that C is in, and I'm left with this 2x2 DEGH. And then all you're doing is you're taking A, and then you're multiplying it by the 2x2 matrix EI minus FH minus B times this DI minus FG plus C times DH minus EG. So that's just sort of a little memory technique. And this cross product kind of gives you that memory technique. So again, can I get rid of that? Okay. So I would take, so what you do is you write IJK along the top. Second row, you write the X, Y, and Z coordinates of the first vector. Bottom row, you write the X, Y, and Z coordinates of the second vector. And then you just use this memory technique. So you start with I, you get rid of the row and column I is left with, and you're left with these two, which in this case is AY, AZ, BY, BZ. Then you're subtracting J, and you get rid of the row and column J is left with, and you have this. So here, I get rid of this, and I have AY, AZ, BY, BZ left. For J, I get rid of the row and column J is in, and I have AX, AZ, BY, BZ. And then I get rid of K, and I'm left with AX, AY, BX, BY. And then you just multiply this out. So it's I times AY, BZ minus AZ, BY minus J times AX, BZ minus AZ, BX plus K times AX, BY minus AY, BZ. So that's just sort of the little formula. And do I have an example problem with me? Boop. Okay, so let's just do this one. So suppose vector A is 3i plus j, vector B, 3i minus 2j plus 2k. What is the cross product of A cross B? So one, this is sort of a generic example because there's no units, right? Any vector's got to have units. But what I'm doing is I'm just setting up, so my matrix is I, J, K, and then I'm doing AX, which is 3, AY, which is 1, and there is no Z component, and then BX, which is 3, BY, which is -2, BZ, which is 2. So that's the setup. And it's always the same. It's IJK across the top, AX, AY, AZ, and then BX, BY, BZ. And then you just sort of follow this formula. So I have I, and I'm getting rid of the row and the column I is in, and I'm left with 1, 0, -2, 2. Then you're subtracting J. You're getting rid of the row and column J is in. So I'm left with 3, 0, 3, 2. And then plus K. And I'm getting rid of the row and column K is in. So 3, 1, 3, -2. And then you're just multiplying this out. So I've got I times, let's do this in I times 1 times 2 minus 0 times -2 minus J times 3 times 2 minus 0 times 3, and then plus K times 3 times -2 plus 1 times 3. So what is this? This is 2 minus 0, so this would be 2i minus, this is what? 6 minus 0 minus 6j, and then I've got a -6 plus 3, which is -3, so minus 3k. This would be the cross product of those three vectors. So that's if you're given I, J, K, if you're given them in X, Y, and Z components. Oftentimes, you're just given, let's say, two vectors, like in this case, A and B. And I want to know what is the cross product. Well, the dot product was a scalar, and I didn't have any direction associated with it. And the magnitude was just magnitude of 1 times the magnitude of the second times the cosine of the angle. The cross product, the end result is it's a vector, which means it has to have both a magnitude and a direction. The magnitude is given by the magnitude of one vector times the magnitude of the second times the sine of the angle between it. And the direction is given by something called the right-hand rule. And for that, the direction of the cross product is always perpendicular to the plane that contains the two vectors. So like in this case, if my vector A pointed in this direction, vector B was like this, the plane that contains A and B, the cross product is always perpendicular to it. So in this case,
making a third axis in a way.
right. And you just need to determine, is it perpendicular, in this case, straight up or straight down? And the way you do that is you take the fingers of your right hand and you curl the first vector into the second vector. Your thumb points in the direction of the cross product. So like here's my vectors A and B. If I took my right hand and I curled A into B, my thumb would point straight up. So that's the direction of A cross B. On the other hand, if I took B and I curled it into A, then my thumb would point straight down. That would be the direction of the cross product of B cross A. With fingers of your right hand, your thumb points. So that's the big thing that you need to know for cross product. It's a vector, which means it has both a magnitude and a direction. If you're given just the magnitudes of each vector and their directions, easiest way to get the magnitude is magnitude of 1 times the magnitude of the second times the sine of the angle between them. And then you figure out the direction by the right-hand rule. If you are given x, y, and z components of each vector, then you're going to end up using this sort of matrix technique to figure out what the cross product is.
Okay.
The reason we end up caring about this, I'll get to this next week, is torque on an object depends upon the cross product of the force and, well, it's R cross F, which is how far away the force, well, I'll get to that on Thursday, but we care about it because of torque.
Could you go over the right-hand rule thing again?
Yeah, I was trying to figure out, I don't know how to do this because I'm not even sure if my image is mirrored, but let's do a different one. Okay, so I kind of went through this in terms of unit vectors also. Let's say I had a vector that pointed straight up, and let's call this vector A. And vector B was at some angle here. If I were to take A and curl it into B with my right hand, what direction would your thumb point?
Upwards.
Like if I'm looking at my screen and I'm taking A and I curl it into B, my thumb is pointing towards me or out of the page.
Right.
So in this case, A cross B is out of page. And just so you know, the way we indicate that is a vector that's coming out of the page. You draw that with a dot with a circle. If you had a vector which was going into the page, do I have that up here? So let me just say if I took B cross A, now with my right hand, if I curled A into B, then my thumb would point into the page. So B cross A is into page. The way we represent a vector which is going into the page is an X with a circle in it. And the little way to memorize this is if I shot an arrow towards you, you would see the point of the arrow coming towards you. If I shot an arrow away from you, you would sort of see the crosshairs of the tails of the feather going away from you. So as another example, let's say that A pointed to the right, let's say A pointed straight up, but B, let's say, was out of the page. So A is pointing straight up, B is coming towards you. If you took your right hand and you curled A into B, what direction would your thumb point?
Into the page?
Well, one, it's always got to be perpendicular to the plane that contains both. So it's still tough. So if A is here, what's the best way of me to do this? A is here, so here's A. Here is vector B, which is coming towards me. I'm taking A, I'm curling it into B. In this case, my thumb points to my right. So if I'm looking at the screen and A points up and B comes towards me, taking A and curling it into B, my thumb points to the right. So in this case, A cross B is to the right. And one way that might help think about this is, if you're thinking in terms of unit vectors. So here, remember, I is just my x-axis, y is j, k is my z-axis, which is coming out of the page. If I took I and with my right hand curled my fingers I into j, my thumb would point out of the page. And so I cross j is k. On the other hand, if I took j and curled it into I, then my thumb would point into the board, which would be the negative z-axis, so it would be negative k. So there's this little memory technique for remembering what is the cross product of unit vectors. And it's this. I draw a little circle, I, j, k, and I have these arrows going clockwise. If you go in the same direction of the arrows, the result is a positive sign. So I cross j is positive k. J cross k is positive I. K cross I is positive j. And if I were to do the opposite direction of the arrows, so if I took j cross I, I'm moving in the opposite direction of the arrows, j cross I would be negative k. I cross k would be negative j. K cross j would be negative I. So just as a little way of remembering this, or at least getting clear with the right-hand rule, see if you can, for all of these different unit vectors, sort of make sense of it. So like if my x-axis points to the right and my y-axis points straight up, if I take A and curl it into B, my thumb would be pointing towards me, which in this case would be the positive z-axis. It's really hard to teach online. I don't know the best way of showing you this. Like in class, I would have had people taking pens and putting them together and things like that. But yeah, does that help at all?
Yeah.
Yeah, what I recommend is going back and watching that cross product video at some point. Definitely will be something that I would quiz you on, or that would be on the final celebration, because you're definitely going to need to know it in physics 4B. You use it all the time.
All right. Sounds good. All right. Thank you.
All right, you're welcome. Other questions I can answer? Hey, Joe, for the at-home lab, can we work with other people? Oh, good question. So you may work with one other person, is what John and I are deciding upon. So you can either work by yourself, or you can work with one other person, as long as both people are, you know, doing the work, and it's not just one person doing all the work. If you're going to work with another person, you may do the video presentation together if you're both sort of on Zoom at the same time. But if not, then you would each need to write your own formal lab report, or each person do their own video unless you're doing a video together. Should be fun. I'm kind of excited to see what people come up with, and it's going to be challenging. Like,
I have a question.
Yeah, what's up, Maria?
Hey, so I was watching your last video this morning, the one you did yesterday, and you do an example problem for the DVD problem.
Yes.
And I was confused because I was not getting the same answer, and I was like, the last part, it's like, I don't remember the number. I wish I had written down the number, but basically,
let me look at it. It's possible I made a mistake too. It was example problem, the DVD, no, where was it? Problem 443, starting from rest, the DVD steadily accelerates to 500 RPM in 1 second.
yeah.
It gets to this angular speed for 3 seconds and then decelerates to a halt in 2 seconds. How many revolutions did it make?
Yes.
Okay, well, let me just check the math. I haven't done it. So one, anytime we're doing these equations of constant angular acceleration, everything has to be in radians per second. Oh, so that was a mistake here. This should have been radians per second. Where's my pen? So if I wanted to convert 500 revolutions per minute into radians per second, I know that in 1 revolution, there's 2 pi radians. 1 minute, there's 60 seconds. So if I multiply by 2 pi radians over 1 revolution, revolutions cancel out. I multiply by 1 minute over 60 seconds. The minutes cancel out, and I end up with units of radians per second. So
Also, I have a question for that part. Like, couldn't I just say, okay, convert it to revolutions per second and then multiply that by the 3 seconds that it's...
Good question. The answer is no. You have to do everything in radians per second because, what's the easiest way to explain that? So let me just say no. How's that? Everything, when you're dealing with angles, you want to do it in terms of, let me think, revolutions, omega naught. Let me think about that. I never do it. Let me go back to this. Where did I do this problem at? If I were to just do all of this into revolutions,
Well, just that middle part, because like that middle part, you have a constant angular speed.
Right. So let me just say there'll be some situations where that might be okay. But as a general rule, anytime we're dealing with angles, especially when we're relating angular quantities and linear quantities, you want to be in radians because, like if we're relating my tangential speed is r omega. This has to be in meters per second. My radius is in meters. This has to be in radians per second in order for the units to work out. If I had revolutions per second, that wouldn't work. So if some of these equations were constant angular acceleration, it would be okay if you did it in terms of revolutions, but to be on the safe side, I would always convert to radians per second and then go from there. So this was a 3-step problem. Remember, anytime the acceleration changes, you have to do another step. So for this one, it started off at rest. It sped up to 52.36 radians per second in a time of 1 second. And so I just have all these same 4 equations that we had for linear quantities, we also have for angular. So if I wanted to know how many revolutions or how many radians did it rotate through the first part, I can use theta equals, or theta minus theta naught equals 1/2 omega naught plus omega times t. Kind of like what I did here. I can find my initial angle to be 0. It started from rest. So I end up with this theta equals 1/2 omega t. And let's just check those numbers. So clear 0.5 times 52.6 times 1. Clear.
Isn't it 50? I don't think it's 52.6.
Oh, 52.36. Aha. So that was just a mistake. 52.36 times 0.5, 26. So 26.18. So yeah, this should be 52.36. But this value here is right. And then in part 2, it's slow. What does it do in part 2? It's, oh, now it continues at that speed for 3 seconds. And so I, again, can figure out how many radians does it rotate through. I'm going to use this theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And again, I'm just going to let theta naught be 0 again, and then just add all of my radians together at the end. It's got no angular acceleration. So I just end up with this theta equals omega naught times t. So 52.36 times 3 seconds, 157.1. So yeah, this answer is right. And then for the final part, now it takes 2 seconds to come to rest. And again, I want to figure out how many radians did it rotate through. Again, I could use this equation where, in this case, it ends up at rest. And so what I end up with is my theta is 1/2 omega naught times t, which 52, that should be 52.4 radians, or 52.6. I don't know why it's 52.4 here, but 52.6 radians. And then all I'm doing is just adding all 3 of these together. So 26.2 plus 157.1 plus 52.6, I get 235.9 radians, which then when I divide by 2 pi, gives me 37.5 revolutions.
Oh, you know what I was doing wrong?
What's that?
I was dividing by 2 pi, but I wasn't putting it in parentheses.
Oh, dividing by 2 and then, there you go. All right, I have to stop. My daughter will be here in like 2 minutes. Thank you, everybody. There will not be, so there will be a video lecture tomorrow. I will get it posted as soon as I can, probably by 11 or noon. And I'm just going to describe sort of what the lab is going to be for the next 2 weeks. And again, it's going to be you creating your own at-home lab to investigate some principle that we've looked at in Physics 4A. All right, thank you all. Happy Tuesday. Office hours done.
Thank you.
You're welcome. Have a wonderful day, everybody.